Hello, I am Ismi and I will be presenting our work Privacy in Urban Sensing with Instrumented Fleets using Air Pollution Monitoring as a use case. This work will appear in Network and Distributed System Security Symposium NDSS 2020-22. The organization of our slides are as follows. First, we introduce the privacy problem. Then we discuss the threat model and the system goals. Next, we discuss the solution of using interpolation, differential privacy, and finally we discuss our end-to-end systems, its pros and cons. And then last but not the least, we discuss the implementation and the conclusion. To introduce the problem of privacy in urban sensing, consider a scalable sensing of particulate matter. Here, to measure air pollution, cabs of transport partners are fitted with PM sensors which measure air pollution, GPS sensors to tag data location. Cabs measure pollution value as they roam around the city. Sense data is then sent to private cab company server. When a client queries a particular location, the server answers with the PM value. But what about if the query location does not have any particular value? That in that case, the server has to answer that there is no value. However, this gives rise to utility as well as privacy problem. Utility problem is that the legitimate clients like commuters or environmentalists wants the server to give response to each and every query. The privacy problem for server is that server does not want to reveal the location of cabs and fleet size, as this will reveal their business model. This gives the underlying threat model, where cabs acts as a data provider and wants to know about the query location of commuters, environmentalists, whereas rival company acting as a data consumer wants to learn about the business model of transport partners. That is where are no cabs or where the cabs are high in demand. To protect the privacy in such scenario, we release the data securely by balancing the privacy, latency, and accuracy. Recall, when there is no cab at a particular location, the response server gives out is no val. We can avoid it by using an interpolation technique, that is Gaussian process regression, where each get centroid gives out a tuple, that is an interpolated value and a confidence in the interpolated value. The posterior mean is representing the interpolated pollution value, and the posterior variance is representing the confidence in the interpolated value. Here we have to see that what is the computation cost. So for server, it will be doing the training and inferencing, while for client, it will be the computation of query function. While what about the privacy? As we see that client does not send its query location to the server, it gets complete privacy. However, from the plots we can see that the cab locations can be discerned by posterior variance plots represented by the dark blue regions in the graph. Posterior mean does not show the direct correlation with the cab location, and hence we do not see any exact cab locations in the posterior mean graph shown in the middle. To prevent leakage in posterior variance plots, we apply differential privacy. Existing solutions apply DP on GPR posterior mean but not on GPR posterior variance. Here, however, we need to apply DP on GPR variance plots as it leaks the trajectory information. We use Laplace mechanism to provide the differential guarantees. to our function posterior variance. We see that after applying DP, we can release differential private maps. However, as DP introduces noise in the system, we have to consider the accuracies. Computational complexity remains same for remains similar to what we have seen in the interpolated maps for server. And for client as well, we don't need extra computational requirement. And the client privacy also remains same, as we are not giving out any input locations to the server. However, we see that as we vary epsilon to achieve different privacy accuracy, we can see that for epsilon equals to 10, we still make out the location information from the graph shown in the middle. However, reducing epsilon degrades accuracy as we introduce more noise into the system, but we get higher privacy. We see that as we start to increase the noise in the system in the DP maps, we start to lose the accuracy, and hence we cannot use that in a real scenario. This motivates us to use secure two-party computation, where two parties compute a function on their private inputs. This computation only reveals the output of the function, and all the other intermediate computation and input remains secret for both the parties. Secure 2PC give us our final end-to-end secure query response system. Here client does not get full privacy, instead it generates private query location vector. This vector hides the location information for which client is interested. Client then communicates with server in an oblivious setting to get query response. For each query, server sets a threshold on the size of client input vector to prevent single length query generation. It also applies DP in secure circuit to protect against smartly crafted queries. For more detailed information of this circuit, please refer to our paper. As 2PC is compute heavy, so uh, we need to examine the cost of communication and computation of our query response system for different supported queries. In our query response system, we handle a number of query functions such as average, minimum, count, range. Computing query function for the uh, solution value is or the posterior mean value is straightforward. But what about the posterior variance? How do we compute that? So we employ the error propagation methodology to compute variance for each query. But error propagation can only be applied on differential functions. We have to see uh, uh, for each function type, we need to find the optimal differentiable function for each query and then differentiate it to get the error functions as seen from the slides. Next, we evaluated our system using the following configuration, where we use two types of client. One was a mobile client and the other is a PC client. We also use EMP toolkit to implement our garbage circuit, our query response system. We evaluated query response system on Porto-Taxi dataset. From the graph, we can see that 80% of the trips are less than 50 km, which corresponds to client query location length of 100. For performance measurement, we measure the latency, the bandwidth. We see that if the average query is the fastest query, as it is simpler in terms of calculation. It has a response time of few seconds for mobile and sub-seconds for laptop user. We also see the CPU usage and the energy power consumption of, in the case of mobile, where we see that the 10% CPU utilization for a heavy range query for length equals to 100. Finally, we summarize our work as first we presented the privacy utility trade-off for fleet companies and sensor data clients. We first applied GPR to hide locations without vehicles. The GPR output variants still leak out fleet location information. We then use 2PC to answer queries with GPR output at low latency and bandwidth for mobile clients, preserving the client privacy and fleet privacy with an optimal data utility. We additionally use differential privacy on the 2PC results to protect against the smartly crafted 2PC queries. We also empirically motivated the use of 2PC by showing that applying differential privacy on GPR output cannot balance the privacy utility trade-off. We also implemented a pollution-aware Android root app, which shows a glimpse of how scalable data sharing can aid citizens to make more informed choices and reducing personal pollution exposure. Thank you. I will be very happy to take questions now.